All right, we've got an introduction here to sequences and series, and we will end up moving on after this introduction to two specific types of sequences and series. What we have are the arithmetic and the geometric. But generally speaking, what we have when we refer to a sequence is an ordered list of items that we call terms. We'll actually use the same jargon when we talk about a series in a little while here. We can have an infinite sequence, so infinitely many terms. We can have a finite sequence, a sequence that stops after a certain number of terms. And when we refer to these, the easiest thing for us to do is to have some sort of index to those. Most naturally, first term, second term, third term, fourth term. So most often, we will have some sort of variable like the letter n is a popular one. I's and J's are also popular. We'll have an index letter, and usually it will start at 1. So literally index, first term, starting with 1, index 2, second term, index is 3, third term. We could also instead start with a different index, and you could kind of think of it this way. Before you do something, sometimes in the instructions they say you're going to need a screwdriver and a drill and a 1/4 inch drill bit. And so you can kind of argue like step 0, let's collect our tools together. And then step 1, literally they go, all right, start doing this. So we can make that same sort of argument that we could also start with an index of 0 and have that be the first thing in our sequence. So index of 0, first term. Index of 1, second term. So that means that we would need to make sure we're paying close attention to how those index numbers are going to be listed. Are they going to start with an index number 0 for the first term? Are they going to start with an index number of 1 for the first term? We're going to want to make sure that we recognize that from whatever information we're given. Now, there are two different ways of defining sequences. We have the first, the explicitly defined sequence, and this is kind of what we're used to from having functions. We have constants, we have variables, and we basically can take a number, plug it in, jam out an answer, and that's that. That's the same sort of deal that we're talking about here. So we're kind of just readjusting what we've seen with functions and going, all right, so instead of a continuous spectrum of y values that come from a function, we're going to look at only finite and discrete values that are going to come from some sort of equation, some sort of relationship. So down here at the bottom, pull up the example that we've got here to illustrate this. Find the first 5 terms of the sequence given by the equation or the formula a subscript n, a sub n, equals -1 to the power of n divided by n. We literally have a relationship here that says I only need numbers and I only have a reference to the index n. There is no other reference to any other term in my sequence. I don't rely on any other information than what index do I have that I would need to plug in, and that index number that I'm going to use is going to generate what term I'm looking for. We can't, in this particular relationship, use 0. So this is automatically limited to starting with n equals 1. Plug that in, get our value for that first term. N equals 2, plug that in, get our second term. N equals 3, plugging that in, getting our third term. When n equals 4, n equals 5, getting our fourth and fifth terms in that particular sequence. And one of the important aspects and one of the skills that you're going to be expected to start using is the ability to recognize a pattern. So one of the important things about this particular example that I wanted to illustrate here is that we have this alternating pattern, positive and negative, terms that are showing up here. So the fact that those terms are alternating between positive and negative is an important observation to make. If we had just been given a list of terms and we were asked to try to come up with some sort of formula to represent that, when we have terms that alternate between positive and negative, that's going to refer back to something like this, a negative 1 raised to a power. It may or may not be a power of n. One of the other things that we can observe here is that all of our numerators also will just have a 1 in them. There's no other sort of number that's coming up. And the denominators are all directly based on our index values that we've got going on here. So one of the things that we might be expected to do is we might be expected to take a listing of terms in a sequence and come up with the formula. Now that's going to be based on pattern recognition, so this is something that they are going to be challenging you to come up with. A characteristic that we would want to consider, because at some point it may be important to know what sort of larger pattern is happening with a sequence. Is it getting closer to a set value? Is it decreasing and getting close to a set value, increasing and getting close to a set value? Is it increasing and just kind of blowing up, never getting close to anything? Is it decreasing and, again, just kind of blowing up, never getting close to a particular number? And the idea here that we're talking about is referred to as convergence. A sequence converges, it approaches a set number. So it can do that by increasing, it can do that by decreasing, it could in fact do that by kind of bouncing back and forth. The other situation, though, would be that that sequence just kind of explodes in our face. Again, whether it's getting larger or getting smaller, it just kind of explodes in our face. It never actually approaches any particular number. It could also kind of do a little bit more of a fancy sort of explosion where it's bouncing back and forth between big and small and big and small and just getting bigger in terms of the difference, just kind of, again, exploding in our faces about this idea here. So if we come back and look at that original example that we had for an explicitly defined sequence, and we've got these particular terms in our sequence, our first through fifth terms, negative 1, 1/2, negative 1/3, 1/4, negative 1/5. And if we keep on looking at things, basically what we've got, these are bouncing back and forth between positive and negative, but they're also getting closer and closer to 0. So we could say that they're approaching 0 and that this sequence would converge. But if we look, for instance, at a different sort of sequence like this one here, where we seem to be looking at the odd numbers, 1, 3, 5, 7, 9, these are the odd numbers that we've got, and based on that pattern, it would seem like the next number after the 9 would be an 11, and then the next one would be a 13. That these numbers are just getting larger and larger. They're never going to converge. They're never going to get close to a single number. They are going to just explode in our face by getting larger and larger in the positive sense. So, to literally write that down, these values are getting larger not approaching a particular number. So we would say that this sequence diverges. This is again something that in a fashion uses that pattern recognition, a different sense of it, rather than coming up with the specific sort of pattern that has to be happening, kind of just overall in a more general sense, what sort of pattern is emerging here from what we've been given, whether it's being given several terms or whether it's being given a formula and being able to come up with several terms, see what kind of overall kind of larger pattern is happening. And again, going with two different basic possibilities of what could happen. I could get close to a particular value, or I could just have my sequence blow up in my face and not have that approach occurring. Now, the second kind of sequence that we have, other than the explicitly defined, the one that kind of most closely goes along with our algebra basis of functions, would be one we call recursively defined. That means, by saying recursively, that it calls back to other terms, could be one, could be several, but calls back to other terms for us to build future terms. So rather than only relying on fixed numbers and some sort of letter for our index, this would be something that refers back to other terms. And maybe the only way of building some sequences would be referring back to other terms, that there might not be an explicit definition for some of the sequences that we would have been given as recursively defined. The most famous of these would be the Fibonacci sequence, which starts out by saying, we will assign the first term as the number 0, we will assign the second term as the number 1, and then each additional term will come from adding the previous two. So that's what this relationship is telling us. The n term comes from n minus 1, the term immediately before, and n minus 2, which is the term also before that. So the previous two terms, the previous term and the second to previous term, I don't know how you would really adequately refer to that one. The previous two terms added together give us what we are looking for. So if we take the original two terms that have been given to us and add those together, those will give us our third term. In order to find the fourth term, we would be adding the third term and the second term together. The fifth term would be coming from adding the fourth term and the third term. The sixth term would come from adding the fifth and the fourth term together. The seventh term would be coming from adding the sixth term and the fifth term together. And so on. So 8 plus 5 is 13. 13 plus 8 is 21. 13 plus 21 is 34. 21 plus 34 is 55. 55 plus 34 is 89. 89 plus 55 is 144. And again, we could continue with that pattern. Now, one of the reasons why I've built up so many of these is because we can take these numbers and actually build another kind of recursively defined sequence. And again, there's a method to this madness here. Bear with me. What we've got so far, coming back to that idea of convergent or divergent, these numbers are getting bigger and bigger and bigger. So this would be considered divergent. Now let's consider a different sort of sequence that we are going to build using a ratio. We're going to use those Fibonacci numbers, and we're going to take a later Fibonacci number and put it over top of, divided by the one that comes immediately before it. So this is what this is saying. The first term of this new sequence is going to come from, well, on the bottom, the first Fibonacci number, and on the top, the second Fibonacci number. Now, we can only do this after we have an index of 2, simply because going back to those Fibonacci numbers, we're not going to be able to have a 0 on the bottom, so I can't do a 0 on the bottom with a 1 on the top. The first thing that I can start with here is my second Fibonacci number. My second Fibonacci number was defined as the number 1. So that's the best that I can do to start things out. So this is partly an example where our index is actually starting at a different number than a 0 or a 1, which again, that can happen. It might not be a commonplace thing, but it can happen. In fact, we can do whatever we want. We could start with n equals 10. Nonetheless, other than that though, let's see what actually happens here as we start looking at what's going on as we begin to put these numbers together into these ratios. So we've got a 2 over 1, which is 2. Then we would have, if we keep on going with that pattern, a 3 over 2. And we're going to be looking at the decimal values, so we'll go ahead and pop those in when appropriate. And then moving on, we've got 5 over 3, which is approximately 1.6666. I think we can go ahead and throw in that repeating decimal bar if we really wanted to, or we can just go ahead and kind of shut things down after about 3 decimal places just to get the idea across. Then the next one, 8 over 5, so that we would have 1.6. Then the next one would be 13 over 8. Excuse me. So 13 over 8 would be, well, I don't recall that one off the top of my head, so we'll just go over to the calculator and bang that one out. 1.625. All right. 21 over 13, and certainly not going to do that one in my head. 1.615, just carrying that out to 3 decimal places. 1.6, what was that? 1515. The next one would be the 34 over 21. So 34 over 21 is approximately 1.619. And then from the Fibonacci numbers that we had at the very end of our little list, so we're kind of jumping ahead, we had a 144 over, what was that, 89? It was 89. 144 over 89. And that would be approximately 1.618. Now, if we looked a little bit more at what goes on in between, we would see a little bit more fluctuation here, but it looks like now we're really starting to hone in on our decimal places here. But looking at the decimal versions of these, 1.6, the couple here towards the end that we were looking at have a second decimal place of 1. The third decimal place, a 5, a 9, an 8. It looks like these are actually starting to narrow in on a particular value. And it does. What we actually have going on here is a special number that is the number that we're converging to. And that particular special number is represented by the Greek letter phi, and that is referring to something that you may have heard before. The golden ratio. You can actually look up a decimal version of that. This is actually one of the numbers like pi and like e, though, that does not have an exact decimal representation. That particular number, like pi and like e, can only be represented exactly in a nice and brief way by using a special symbol. So other than the Greek letter pi or the letter e, we now have the Greek letter phi to represent another one of these very special types of numbers. Now, to just kind of give a little side note, there are some other sorts of things that we can use in creating sequences and series, and you can see down here at the bottom we're about to mention what series are in the first place. But one of the other things that is common to sequences and series are what we call factorials. No, this is not exciting. 4! No, 4 factorial. It's my standard joke. So, 4 factorial. What we have is a definition here. This factorial business is a shorthand way of referring to, I want a string of whole numbers that are multiplied together, and I can even kind of try to one-up that definition and apply it to some other things. We're not going to do that, but I could try to, expand that idea to, what would I have if I had a fraction followed by that factorial symbol? And anyways, point being, there are some of these specific sorts of patterns that happen to show up, so it's nice to be able to have a shorthand for those. So when we've got a string of numbers that are being multiplied together and they're all in a row, they're kind of all counted out in a nice sort of natural fashion. 1, 2, 3, 4, 5, 6, 7, 8. If I just start multiplying stuff together, 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Well, it'd be nice to have a shorthand for that because that gets very, very long, very, very quickly. So the factorial is what does that for me. 4 factorial. 1 times 2 times 3 times 4, stop, because the 4 is what shows up there in that factorial. The example that I used just a moment ago, 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. That's a factorial. Stop at the 8 because that's the number that shows up with that factorial symbol. And if we multiply that out, we get 40,320. We start actually working with things by saying, hey, if I put factorials on the top and on the bottom, well, standard sort of rules for reducing fractions. If that top is all expanded out, then the last stretch of that numerator is actually the same as the 5 factorial down there on the bottom, so that actually just reduces down to an 8 times 7 times 6, which I can do as well by hand by saying, all right, the 15, I can start breaking off the 15 times the 14 times the 13, and then say everything else after that would be officially shorthanded as 12 factorial. I stop there because that's exactly what I happen to see down on the bottom, 12 factorial, and so I can come in here and say the 12 factorial on the top and on the bottom would reduce out, leaving me with the 15 times 14 times 13. We're going to get an answer for that in just a second, but I also want to show you very quickly that the factorial is something that you can type into your calculator, kind of have your calculator do the grunt work for you. So let's go ahead and clear this stuff out of the way real quick. In order to bring up the factorial, first of all, we're going to type in the number that we want. So for instance, in this case, let's do that 15 factorial over 12 factorial. So up there on the top, I want the 15 factorial to show up. My factorial can be found in my math menu. So on the left-hand side of my calculator, click the math button. And then normally that factorial business shows up in reference to what we have in math called probability. Now, that's where it might show up more often. However, it does show up a great deal with the sequences and series. So rather than creating a brand new menu, that's just where we can find it. So option number 4 here, if I select option number 4, that will automatically insert that factorial symbol. And since we want to do that little division problem, then we're also going to go ahead and put in the 12 with the factorial, and then we can hit enter so that it would come up with that correct calculation for us. If we separately did the 15 times the 14 times the 13, we should get the same answer. And lo and behold, we do. 2,730 is the answer that we would get for that. So this is one of the other things that may show up in some of the sequences and series that we have to deal with. And so in case it does, we have this basic definition as well as some calculator components that we can utilize. But here at the very end, since we're talking about an introduction, let's talk about very quickly what it means to be a series. And basically what we're going to do is we're going to say, while a sequence is just a list of terms, a series is going to be the sum of terms. So we kind of say, all right, look, if I take a sequence and everywhere I see a comma, I put in a plus sign. Then what we would have constructed there is a series. Series can also be infinite, or they can be finite, so they refer to some sort of partial sum that only goes up to a certain index value. Generically speaking, nth partial sum, that's going to stop at some index number n. We can shorthand that summing process, that summation, by referring to a starting number on the bottom of a capital Greek letter sigma, sigma s, sum. So that's why we've got that particular letter being used. So at the bottom, they tell us what index letter we're going to use. They tell us what starting index number we're going to use. At the top, they would tell us the ending value for our index. Now, if this was an infinite sequence, or excuse me, an infinite series, we would use an infinity symbol up there to represent that. I'll show you that in a minute in one of our examples here. So again, generically speaking, since that top is not an actual number, it's just the letter n, that's saying stop at an index value of when I equals n. Infinite value, there's the infinity symbol up on the top to say that we're just going to keep on adding and adding and adding and adding. In this particular example, we're going to use a letter J for our index. It's going to start at 1. We're going to add until we get to j equals 8. So when j equals 1, when j equals 2, when j equals 3, so on and so forth until j is equal to 8. And we could literally add all those up. So with the assistance of our calculator, typing in those fractions, adding them all up, and then even using our calculator to convert that. And it's probably likely going to be a decimal answer that they show you at first. Take that decimal answer, use your calculator to convert it to a fraction, 255 over 256. Similar sort of expression here, but showing you that different starting values start when n is equal to 2. Okay, so 1 over 2 squared, then 1 over 3 squared, then 1 over 2 squared, 2 to the power 3, 1 over 2 to the power 4. That pattern would continue, and because up on top we do not have a number or a letter, we have the infinity symbol, that pattern is going to continue forever. So this would be an infinite series. There are a couple of issues, a couple of exercises here in the homework where they basically ask you, try to get used to this notation by basically adding, 3, 4, 5, 6 terms together. So they try to keep it mellow, but still give you a little practice reading what this is referring to and using those formulas that show up. And we're going to see this sort of thing again, specifically in the context of the arithmetic and geometric sequences and series that we're going to look at, each one individually in its own separate video. So this is the introduction that we have to the different sorts of notation, the different sorts of ideas overall that we would be concerned with as related to sequences and series.